Hello everyone.
Hi.
Hi, YouTube.
This is the lesson on section 2.1 and section 2.2. It's on limits. Are you ready?
Yes.
Baby.
Yes.
Here we go. First, we're going to find limits graphically. And so example 1 is all filled in for you. And period 8, I'm going to send a PDF of this to you guys. Example 1. If you remember, when it says the limit as x approaches 1 with a superscript of a plus sign right there, that means that you're approaching a x value of 1 from the right. So here's 1, so you're approaching 1 from the right. As you do that, the question that this is asking is what y value are you approaching? So let's say that you are a person walking along this graph and you're walking towards an x value of 1. What y value are we approaching? Well, it appears that we're approaching a y value of 2. So the limit as x approaches 1 from the right of f of x equals 2. Now we're going to approach an x value of 1 from the left, this way. So pretend you are walking along this graph from the left side of x equals 1, and you're going this way. What y value are you approaching? Well, it appears that you're approaching the exact same y value, also 2. So this one is 2. When there is no superscript, when it's just limit as x approaches 1, what are we supposed to do? Approach from both sides at the same time. And it happens that they both approach the same y value of 2, so that limit is also 2. And then, now we're going to approach x equals 2. Now, approaching x equals 2 is similar, but there's one thing that's a little bit different. When we approach 2 from the right, we are approaching an open circle. And I estimated this to be 2.7. What y value are we approaching? 2.7. The key here is the approach. We never attain a y value of 2.7. But that's not what the limit is asking for. The limit is asking for what y value we are approaching. So whether or not we actually get to 2.7 doesn't affect the limit. So from the right it's 2.7, from the left it's 2.7, from both sides at the same time will be 2.7. Okay? So with that in mind, we're going to march through the rest of this page pretty quickly. Okay? All right, so this example 2, as x approaches 3 from the right, this open circle is at 2, so this will be 2. Notice that notice that right here tells us that f of 3 equals 5. What relevance does that have? Nothing. This is not relevant to finding the limit. Okay? So whether this point is up there or it's not up there, or even if that point is filling in that hole, the limit is not affected. Okay? Alright, what about as x approaches 3 from the left? What y value are we approaching? 2. So approaching 3 from the left and right at the same time? 2. What about when x approaches 0? This one doesn't have a superscript. So we are kind of jumping a couple steps and approaching x equals 0 at the same time. So from the right, we're approaching a y value of 3. From the left, we are approaching a y value of 3. So from the left and right at the same time? 3. Next, as x approaches infinity. Okay? As x approaches infinity. This one, we're going to approach infinity that way. What happens to the y values as x approaches infinity? It's getting larger and larger without bound. So this will be infinity. Okay. What about as x approaches negative infinity? The graph is going down, decreasing, or it's going downwards as you go to the left. So this is negative infinity. Okay. Example 3. This one introduces what in it?
Asymptote.
A vertical asymptote. This is introducing a vertical asymptote. It's also introducing a horizontal asymptote. Where?
0.
On the left side right here, y equals 0. So can you have a horizontal asymptote that only applies to 1/2 of the graph?
Yes.
Yeah. All right, so let's look at this one. The limit as x approaches 2 from the right. So I'm approaching 2 from the right. This graph is going towards negative infinity. As x approaches 2 from the left, this way, so we're on this part of the graph. What are the y values doing as x approaches 2 from the left? Approaching infinity. Good. As x approaches 2 from the left and right at the same time, does not exist because the two do not agree. Okay? Does not exist. Okay?
It exists in my heart.
All right. As x approaches 0 from the left and right at the same time. So we're approaching 0 from the left and right at the same time. Are they approaching the same y value?
Yeah.
Yes. We'll just estimate this one. That looks like it is
1.69.
1.65.
Okay.
What? That doesn't make any sense.
Oh, sorry. 0.65.
I'm sorry, Mr.
I
A.
put 2/3, that's pretty close.
Yeah. So. Or, if we really want a better official answer, what do you think it would be?
Half of 0.
K of 0. Because this function is called K.
Oh my bad.
Okay.
Alright, what about as x approaches infinity on this one? Infinity, and as x approaches negative infinity? 0, because the y values are approaching 0 as you go further and further left. Alright, now number 4 introduces yet another obstacle. What is number 4 introducing us?
Slide discontinuity. I forgot what it's called.
Discontinuity.
Movable discontinuity. It's not.
Jump. 2 lines.
Jump. Introduces us to a jump. Okay? Alright, so did we already see a hole or removable discontinuity?
Yeah.
Yeah, up here. This introduces us to a jump. Alright, as x approaches infinity this way, what's the graph doing? Infinity. As x approaches negative infinity this way, what's the graph doing? Negative infinity. As x approaches 1 from the left, so we are going 1 from the left, so we're on this part of the graph. So if you're walking along this part of the graph, what y value are you approaching? 4. Do you ever attain a y value of 4 here? Yes, you do, but that doesn't matter that you do. Okay? Okay, now we're going to approach 1 from the right. So you're on this part of the graph, and you're walking this way. What y value are you approaching? 2. Do you ever attain a y value of 2? No. But, once again,
Doesn't matter.
it doesn't matter. Okay? The limit is what is being approached. Okay, and finally, as x approaches 1 from the left and right at the same time, does not exist because these two don't agree. Okay. A limit has to be a single numerical value or it doesn't exist. Okay. Now infinity and negative infinity are not values, so they are specific types of limits that don't exist. Okay. All right.
Wow.
So we're going to skip example 5, 6, and 7. So right now, I want you guys to, actually we're going to move ahead because of time. Okay? So when you have time, you can kind of try examples 5, 6, 7 on your own. Okay, let's go to the next page. Finding limits numerically. Numerically means using a table. So over here, I have this formula right here. Now, let me just take a quick period of time to talk about this interesting function. Y equals x squared minus 3x minus 10 over x minus 5. Okay. Now, I can factor the numerator, which will become x minus 5, x plus 2, all over x minus 5. And what we normally would want to do is cancel this and end up with x plus 2, correct?
Correct.
But there is one instance where you're not allowed to cancel x minus 5
At 5.
at 5. Why not?
Because the,
Yeah.
in the
Then it'll
original
be
equation,
infinity.
the original equation, you can't plug in 5.
Yeah. So we cannot cancel this when x is 5. When x is anything other than 5, they cancel. Okay? Another way to think about it is if x is 5, this becomes
A whole
0, right? Now 0 times 7 over 0, is that equal to 7?
Yes.
No, right? So you cannot cancel x minus 5 specifically at the moment when x is 5. Okay? So, what is the difference between these two graphs?
One has a hole and the other one does not.
It's removable discontinuity.
This graph
Removable
looks like that.
discontinuity.
Yes.
This graph is also looking like that, except
There's a hole.
at 5, we have a hole. Okay? Now, what is the significance of this? Okay? Well, for this one, when x is 5, y is 7. So where would be the location of this hole?
7.
At 7. Okay, now, in this graph, the limit as x approaches 5 is what?
7.
7. For this one, the limit as x approaches 5 is what?
Also 7.
Also 7. Because with limits, what happens at x equals 5 is not what we're concerned about. Okay? This is officially called a removable discontinuity. Hole is just an informal term people use, but
What about those
the
points?
proper term is removable discontinuity. Okay?
Like hole.
Now, later on this chapter, we'll talk about why it's named that.
Because you can remove it by putting a little dot. Okay, never mind.
Yeah. Okay. So here, when you make a table, we have an error when x equals to 5. Now, the step size here is just 1. So it says 4, 5, 6, and then 10, 9, 8, and we read the table like this, going this way and going that way. It appears that the y values are approaching what?
Error.
7. But what is more convincing is when you zoom in a bit and make the step size smaller. So you see how we're approaching 5 from the left there? What y value are we approaching? 7. And then going this way, we're approaching 5 from the right, and what y value are we approaching? 7. So is it pretty safe to say that this limit is 7? Yes. What's shown on this paper is numerical evidence. What's shown here is graphical evidence. So you can find limits graphically, like we did in the first 2 pages, or you can find limits numerically with a table like this. Now, you look at this and it's pretty simple, but let's jump down to example 10. Okay.
Balls.
All right, now we have a piecewise function. Let's do a quick 30-second review of piecewise functions. The top piece is what kind of graph?
Linear.
Linear graph with a slope of,
Negative
Negative
1.
with a y-intercept of
Tree.
3. So we draw that, but the only thing that it doesn't apply is at -1. So we just do a circle there because it doesn't apply at -1. Okay? When x is -1, what output do we want?
2.
2. So this is 3. So something like that. So that's our graph. Okay? So we can find the limit here graphically. What would this be? Where is the location of this hole? -1 comma.
-1, comma 2.
Close. 4. 3
3
minus -1. All right. So
I'm bad with
graphically, what is this limit?
4.
4. Okay. If we build a table, we would also see that. So these numbers and these numbers, what piece do we use?
3 negative x.
3 minus x. So this is going to be, and we don't need a calculator for this.
4.1.
What's the first one? What is it?
4.1.
4.1, next one?
4.01.
4.001. Okay, now, what about, let's go up this way. Plug in negative 0.9, what do we have?
3.9.
3.9, 3.99, 3.999. Now plug in negative 1 into that function. What is f of negative 1?
Error.
2.
Oh.
Okay? 2. So, as we read the table this way, and as we read the table this way, and we disregard this, what appears to be the limit? 4. So, I'm emphasizing the point that it doesn't matter what is happening at x equals negative 1. Okay? Alright, now, this problem is a famous one, and something that you encountered in PCH.
Lima bean.
It's friend.
What is this called?
Lima bean.
Lima bean.
Yeah.
Okay.
It's lima bean.
Now, Mr. Park's class calls it friend, but I call it the lima bean.
Why can't a lima bean be your friend?
It can be your friend, and your friend can be a lima bean. Yeah. Okay, anyways, how do we do this numerically? We build a table. So everyone, we're going to put a table here. Now there are different ways of formatting this. There's no right or wrong way of formatting it. But the way I like to format it is I like to put the value that we're approaching in the middle. So 0. Okay? And then I want to approach it from the left. So maybe we'll have a point, negative 0.1, a negative 0.01, a negative 0.001. And then I also want to approach it from the right. So 0.1, 0.01, and 0.001. Okay? All right. Because of time, we are going to just put those numbers in. When x equals 0, what do we have?
Error.
Error. Why?
Because anything over 0 becomes an error on the calculator.
Yes, indeedy. So this is undefined. Okay? Okay. Now, if you put in negative 0.1, you are going to get 0.99833. If you put in 0.1, you also get 0.99833. Okay. And then Sydney, can you quickly plug in negative 0.01? Make sure you're in radian mode. And then Gabriel, can you quickly put in 0.001? Make sure you're in radian mode.
Make sure you smash that like button.
0.99998.
Hey Wolfgang, you gotta concentrate.
Okay. So this one will be 0.99998. And then Gabriel, do you have this one?
Good. That's 0.0.
0.001.
0.999999833.
How many nines?
2, 4, 6 nines.
6 nines, and then
Oh,
what's
God.
after? What's after?
Takashi?
6 nines.
And then what's after?
833.
Okay, alright.
Really?
There's one more 3, but it's okay.
Okay, so reading the table this way and reading the table this way, are they approaching the same y value?
Maybe.
Yes, what
Yes.
y value are we approaching?
1.
1. So numerically, we are determining this limit to be 1. And you should remember from last year PCH that it is 1. Yep. Alright.
Lima bean.
Now, graphically, you can graph it on your calculator on your own and see that the limit is 1. Now, a little quick thing right here. And here's why I call it the Lima bean. Let's say I have something that looks like that. Sine 7x over 2x. Okay. In order to apply this limit, I need a 7x in the denominator. Because sine 7x over 7x would approach 1. So it's sine of anything x divided by that same coefficient x. So I need to put a 7 on the bottom. Can I just do that?
Yeah.
If you put on the
As
top.
long as I put 1 at the top, then everything is balanced. Okay? Then you draw your lima bean. And that lima bean approaches
7 over 4.
Oh, that line would be approach is 1.
1. So then you have 7. Okay? Doesn't that look like a lima bean?
It does.
Okay, let's continue on to the next page. Now we're going to find limits algebraically, which means not with a table, not looking at a graph, but by plugging in numbers and doing
What?
algebraic steps.
Sounds horrible.
Okay. All right, so this first one, this is a parabola. The fact that a parabola has no removable discontinuities, no jumps, and no asymptotes makes it the case where the limit is simply
Tree.
the value you get when you plug in the number. And we'll get more detailed into that in 2.3. So this one, you just do 3 squared minus 4 times 3 plus 10. Okay, that's it. 9 minus 12, negative 3, so 7. So the answer here is 7. Okay. This one, same thing. We're going to just plug it in. So cosine pi minus e to the pi minus pi over 4 plus tangent of 3/4 pi. Now I put this in here so that it's a reminder to you that you need to know your trig values right away. Cosine pi,
No.
negative 1. E to the 0 power,
1.
1. 4 plus tan of 3 pi over 4.
Positive. Yeah, negative
Negative
1.
Negative 1. Okay.
See, I'm a bit rusty.
Alright, so that's negative 2/3. So the easiest types of limits to calculate are the ones that you're able to just substitute. So that's called direct substitution. To find limits of a piecewise function algebraically, you have to find the two one-sided limits. So first, this is a piecewise function. We know that one piece is a parabola and the other piece is a line. Here we want x to approach 3 from both sides at the same time. So to examine this, you first have to consider the limit from the left.
Okay, the approach is 5.
Okay. What piece are you on when you are approaching 3 from the left? The 8 minus x. So 8 minus 3 is 5. So you know that those pictures where I drew a stick person and that stick person is walking towards on the graph? That stick person will be walking towards a y value of 5. Now we need to approach 3 from the right. So now you're walking along this graph from the right of x equals 3. What piece are you on?
X squared minus 4.
X squared minus 4. So then it's 3 squared minus 4, which is 5. So what happened? What did these two pieces do?
They're both approach 5.
They're approaching the same y value. They're connecting. And so this limit will be 5. Okay?
The amount of fingers I have.
What if you have 6 fingers? Or 4?
Okay. 5
You have 5 fingers total.
is the answer. Okay, part B. Same thing. We're going to move this along a little more quickly. Okay. What piece?
Is it 2x?
2x minus 3. So plug in 2 into 2x minus 3 and you get
1.
1. Okay. Now we need to approach it from the right. What piece are we on?
Minus x squared
Yeah,
plus 4.
the quadratic piece.
The
So that's negative 2 squared plus 4 times 2 minus 1. And that equals to negative 4 plus 8 is 4 minus 1 is 3. Uh-oh.
Dennis.
On one side, so this is, so what's happening on the graph? There is a jump. So this limit does not exist. Okay. Example 14. Now, all of these have a removable discontinuity. And here's how we know. if I plug 5 into the numerator, what do I get?
0.
0. When I plug 5 in the denominator, I have
0.
0. When you have 0 over 0, first of all, what is that called? What form is that?
That's
There's a name for it.
it's like you can't find it.
It's called indeterminate.
Yeah, okay.
Indeterminate. But what it really means is that there is a factor of x plus 5 that you can pull out of the numerator that can cancel. So it's what we did over here. Okay? So to find this limit, you do what I call factor cancel substitute.
Oh. Can
Are
you
you
sing
gonna
it
sing
for us?
it?
You can ask my students last year, there's a song that goes with it. But I don't want this, my singing to be on video, so you could ask other people. Actually,
Smash that subscribe
Kate
button.
sings it pretty well.
No, I'm not singing it.
What's this? Go
He
for
doesn't
it.
know the lyrics. Yeah. Wait, I just need to refresh it real quick.
Oh, you know it.
No, I think I need to refresh it.
If this video gets more than 500 likes, Mr. Ye will
Okay,
sing it.
so we already talked about this right here. Okay. Why are we allowed to cancel x minus? Let's go back. What did we say was the only time you can cancel x minus 5 and x minus 5?
When it's not 5.
When x is not 5.
And if it approaches 5, it can't beat 5.
Exactly.
Boom.
So we can cancel here because x is not 5. X is approaching 5.
Mhm.
So we're good there. We're allowed to cancel. And canceling is really helpful because it got us the limit. Because, like we said earlier, these two graphs have the same limit. So let's use this simplified version to find the limit. Okay, we're going to skip these down here because of time.
What?
Let's continue to the next page. Okay, now, this is now going into 2.2. And I only have a few minutes to kind of get us going in 2.2. So let's see how far we get. Okay. Sometimes we have infinite limits, meaning the limit is infinity or the limit is negative infinity. What will cause that to happen? What kind? Vertical asymptotes. Exactly. So there are 4 cases that I like to highlight. The first case is when you approach from the left, the graph approaches infinity, and when you're approaching from the right, the graph is also approaching infinity.
It's a volcano.
Yeah. The second case is when you're approaching from the right, the graph the y values approach infinity, and when you're approaching this particular x value from the left, the limit is negative infinity. And I think it's pretty obvious what the last 2 scenario is. Okay. So all 4 of these scenarios will give us infinite limits. But how do we determine, without drawing a graph, what the answer should be? Because all these answers are either infinity or negative infinity. Now let's look at the example down here. 1 over x minus 3. First of all, at the most basic level, everybody knows how that looks like, right? This graph has a vertical asymptote of x equals 3. So then we have, it's going to look like one of those 4 cases. How can you tell which case it's going to be? Well, one strategy is to make a table. Here it says approaching 3 from the positive side. So you go like this. 3.1, 3.01, 3.001, 3. Like that, yeah? And then you see what these numbers are, and whatever these numbers approach will be the answer. Another approach is that we know that this is a vertical asymptote, so we know the answer has to be what or what?
Infinity or negative infinity.
Infinity or negative infinity. So another approach here is to just pick a number really close to 3 from the right, such as
3.075.
when you plug 3.1 in for x here, the numerator is positive, the denominator is positive, making the whole thing positive. So this is just positive infinity. Okay. Part B, x is approaching 3 from the left, so choose a number really close to 3 from the left.
2.987.
2.9, which will, if you put in 2.9 right there, The numerator is positive, the denominator is
Negative.
negative, making the whole thing negative.
Negative.
So your answer is
Negative infinity.
negative infinity. Okay? Alright, we're gonna move on right ahead. We're gonna jump ahead to the page that says limits at infinity of a rational function. Now the bell's gonna ring in 30 seconds, and we have one more minute. Just one more
Yes, sir.
Alright, so here's a rational function, and we worked with this in PCH last year. These types of limits at infinity means we want x to approach infinity. So we're looking at the far right end of the graph, or the far left end of the graph when x approaches negative infinity. And you might remember that what we do is we look at the dominant terms. What term dominates everything in the numerator?
2x to the fourth.
2x to the fourth. How about in the denominator? Negative 5x to the fourth. If we cancel, we get negative 2/5. Okay?
So that's what it
Negative 2/5 is what they call the end behavior model of this graph. This x squared term, that 9 is negligible. The 9 would do barely anything when you're doing infinity, a trillion to the fourth power. Okay? Now this one is a little bit different because what's the dominant term in the numerator? 5x to the fourth. Denominator? X to the fifth. This simplifies to, notice I'm carrying this limit symbol as long as there's an x in my expression. This will be 5 over x. 5 over a million, 5 over a trillion. They will
0.0000253.
the bottom dominates.
Okay? And then finally this one, the limit as x approaches infinity, the dominant term in the numerator is x to the fourth, denominator is x to the third. So this is limit as x approaches infinity of x. And as x approaches infinity, what is x approaching? Infinity. Okay? What is the significance of the number negative 2/5? That's going to be the horizontal asymptote. Y equals negative 2/5. Here y equals 0. And then this one tells us there is no horizontal asymptote. Okay?
There is no spoon.
Alright. Your homework tonight is 2.1, and then your homework Friday is 2.2.
Make sure
So
you have like
try to complete both of those assignments if you can. Okay. Alright.
Make
Have a
sure to
good
smash that like
weekend.
Make sure to subscribe and